now we go to problem 954. Okay, you have this kind of state of stress of this element, right, where you have the tension of 80 megapascal and in this direction, basically x, okay, and then you have the compression of 120 megapascal in this direction, which is basically y, and then you have a shear stress of 50 megapascal, which is in this configuration. So the question asks you to find this by first using stress transformation equation, and then the second one is to find it by using Mohr circle. But in this video, I'm going to show you how we do it by using stress transformation. So what you want to find? The question asks you to find what are the principal stresses and what is the maximum intention stress. Of course, when you find your maximum intention stress, you have to find your average shear stress as well. Okay, for that configuration. Okay, so the first one, let's do this by using stress transformation equation. So first, you need to identify what are all these. What are they? Basically, this is sigma x is 80 megapascal plus, okay, sigma y equals to minus 120 megapascal, right? Plus 80 minus 20 minus 120, and your tau xy equals to minus 40 megapascal. Why minus? Because you look at the right hand side, it goes down, right? The shear stress. Okay. After identifying this, then you know your equation for your principal stresses, sigma 1 and sigma 2. Okay, sigma 1 is your maximum principal stress, sigma 2 is your minimum principal stress, right? So it is given as sigma x, okay, plus sigma y divided by 2, which is minus 120 divided by 2, okay, and plus minus, right, root sigma x minus sigma y divided by 2 squared. So it is sigma x minus sigma y, right? Sigma x minus sigma y divided by 2 whole square plus tau xy squared plus tau xy squared. Okay, you solve this, you get your sigma 1. Okay, you solve this and you will get your sigma 1 and sigma 2 as 87.7, right, and 157.7. Alright, in this case, do you know which one is sigma 1 and which one is sigma 2? Which one is sigma 1, which one is sigma 2? This is sigma 1, okay? This is sigma 2. How do you know that? Like I said, sigma 1 is the maximum principal stress. Sigma 2 is the minimum principal stress. So it includes the positive and negative. In this case, it's positive, so definitely in this negative. So definitely this is sigma 1, this is sigma 2. Right? The most tension, the most compression. That's what I mean. So actually can be both tension and compression, by the way. Okay? Okay, now okay, you have done this, so you need to find the angle now. Tangent to theta p, right? Of course, you will have your p theta p1, theta p2 as well. Okay, tangent to p equals to tau xy, which is minus 40, right? Divided by sigma x minus sigma y. Okay, sigma x minus sigma y, right? Times 2. Okay, this one will give you, okay, this one will give you theta p equals to minus 10.9 degree and 79.1 degree. Okay, you see again you have two angles. Okay, regarding how to get these two angles, you need to find yourself. Okay, you need to go back to this concept. Okay, please go to this concept. You remember first quadrant, second quadrant, third quadrant, fourth quadrant. The first quadrant, all sine, cosine, tangent is positive, right? Second quadrant, all the sine is positive, right? The third quadrant, all the tangent is positive, isn't it? The fourth quadrant, the fourth quadrant is only cosine is positive. So go back to this. Don't ask me. I mean, and then the theta is, the angle is clockwise. Sorry, counterclockwise, right? From this to any point, right? Right. then so what you have to do is you need to try to find out which of these is actually, belonging to what. This one belongs to which one, and this one belongs to which one. Okay. So what you have to do is, for instance, you take this theta equals to minus 10.9, and then you try to put into the general equation. Okay. Alright. The equation is what? Sigma x prime, right? So sigma p or sigma x prime equals to sigma x plus sigma y, okay, divided by 2, right? Plus sigma x minus sigma y divided by 2, right? Cosine 2 times 10.9, okay? Plus tau xy, which is minus 40, sine 2 theta, which is minus 10.9. Okay, what do you get if you calculate this? You will get 87.7 megapascal. What does it mean by this? So theta p equals to minus 10.9 degree. Okay, minus y minus, it is what? Clockwise, isn't it? Sorry, yeah, clockwise. That's why it's minus. This one, it is related to sigma, which one? The sigma 1. Okay, of course, if you put the same thing in this equation again for theta equals to 79.1, we get the other one, which is this. So this one is theta p1, right? And your theta p2 is 79.1 degree, which is related to sigma 2. Okay. That's right. Sigma 1 is 87.7 Pascal, while sigma 2 equals to 127.7 megapascal. Okay. So what's happening here? You will get your sigma 1, your principal stress, 87.7 megapascal. When you rotate the element, minus 10.9 degree clockwise, isn't it? You get your sigma 2 and you rotate it 79.1 degree counterclockwise. Okay, this is for the principal stress. So next we go to the maximum inclination stress. So we are done with the principal stress. Now we want to see how do we get. Oh, we didn't. Oh, forgot. Okay, forgot to do that just now. Okay, so what did you do? You rotate it. You rotate it at 79.1 degree counterclockwise, right? Positive theta p2. Okay, so you got this from x to this one. So you rotate this to 79.1 degree, right? And then what you got is you got your principal stress of compression, minimum principal stress, okay, sigma 2, which is 127.7 megapascal, isn't it? Okay, of course you have this another one here, right? And then the one that you rotate here from x, right, x to this, okay, basically it's just small one, which is 10.9 degree, right? So at this one you got your sigma 1, which is 87.7 megapascal. Okay. How about your shear stresses? No, you don't have a shear stress because this is principal stresses. When you got your principal stresses, sigma 1, sigma 2, there is no shear at this point. And this one are the most. You got your principal stresses, okay? The condition of your principal stresses, where your normal stresses are at the maximum. It's maximum. Okay. Now we go to the maximum implementation stress. So because you're going to just use the equation for this. Okay. So tau max in plane is what? You have the equation for that. Okay. Root. Okay. Sigma x minus sigma y, which is what? Plus 120. Okay. Divided by 2 all squared plus tau xy squared. Square root everything. And then you will get this as plus minus 107.7 megapascal. Why plus minus? Because rule. Okay. Of course, you will have two. By the way, you have two answers, right? And you have to find your average. Okay, because remember at this point where you have your maximum shear stresses, maximum implicit shear stress, you will have the sigma average acting on the faces, on the surfaces, 4 faces. Okay, so it is sigma x plus sigma y divided by 2, which is sigma x plus sigma y divided by 2, right? Which gives you minus 20 megapascal, right? And then to find the angle tangent to theta s, of course you have S1 and S2 as well. Okay, theta S1, theta S2. So it is given as, okay, minus sigma x minus sigma y, okay, divided by tau xy, right? I'm not sure. What's the equation again? Sigma x minus sigma y. Minus sigma x minus sigma y. So okay, divided by 2. Okay, so divided by 2 here. Alright? You got 2.5. Okay, plus 2.5 by the way. Plus 2.5 here. So you have theta S2 equals to 34.1 degree and theta S1 equals to 124.1 degree. Okay, you got these two angles. So of course, if you put theta S2, which is 34.1 degree, into the equation, you will end up with your tau S2 or tau max. Okay, sorry, this one tau max equals to minus 80 minus sigma x minus sigma y, alright, divided by 2 sine 2 theta, which is 34.1, right? Minus, sorry, plus tau xy cosine cosine 2 theta, which is 34.1 degree. Okay, will give you this one, will give you tau S2 as minus 107.7 megapascal. What does it mean by this? So theta S2 actually is related to tau S2, which is this minus 107. Okay, the minus shear stress is related to tau S2. Okay, this is important because when we're going to draw this, we're going to draw. Okay, let's erase this. You have to draw this again. Right? What will happen is, when you draw this, okay, from x, okay, to 34.1, right, which is x prime, okay, you rotate it to 34.1, which is this principal, your maximum implicit stress, the angle for maximum implicit stress, 34.1 degree, right, and then you will get your 107. Going to draw the other three faces, but look at this face. Initially it was like this, right, for x, and then from x it goes to x prime, which is the principal, again, the angle for the maximum implicit stress is 34.1. What did you got? What do you get? You got this minus 107. So that's why on the surface it goes down. It's okay, 107.7 megapascal, but it goes down here on the surface because this angle of 34.1 degree positive corresponds to minus 107. So on this face it goes down, right? The other surfaces, of course, once you got this, actually the rest are just complementary. But of course, if you want to find them, you can, for instance, this one, when you rotate into 134, which is from here to here, and then you will get your plus, which is, you can see that it goes this way, going up, plus, right? Is this complete? No. You have what? You have the average as well, which is minus 20. Sorry, minus 20. Okay, compression 20 megapascal. Right, on all four surfaces. Okay, on all four faces. In the state of maximum in-plane shear stress, we have the average normal stress, sigma average, on all four faces. Right?